Hello, very good evening to everybody.
Good evening, sir.
Good. I hope that we'll be able to make it today. But unfortunately, if you want to understand things very well, we have to also take our time to also understand some mathematics in this whole exercise. And so I'll try myself to finish. If I'm not able to finish, we shall have another slot, but I'll do my best. All right, so the very critical aspect of sperm analysis is the counting. All right, so we will do what we have to do. So the sperm count can also be considered to be concentration. It can also be considered as the density. So when you talk about sperm density or sperm count or sperm concentration, I mean, it's the same thing. Okay, it's a measure of the number of sperm in 1 milliliter, 1 ml of the semen. Okay, and that makes it a concentration. You know how to define a concentration. All right. So the number of sperms in a male and the number is usually in millions. So the number of sperm in millions per male. That's how sperm count is usually defined. It is perhaps the most, people consider as the most important parameter. But as we all know, motility is very, very key. Because if you have the numbers and they are not motile, to what extent can it help in your course? And also, it's been established by WHO that you can have the range from 15 to 259 million per male. And this is where people get it wrong. For example, if somebody can get as much as 259 million per male, what it means is that if such a person in the collection of a sample loses the first portion, and we have all come to know that semen production, and for that matter, the ejaculation occurs in fractions, and the first part takes about, if you lose the first part, you lose about 70% of the sperm count. All right, so if somebody can have as much as 259, all right, and that person even loses the first portion, 70%, it means that you'll be left with just 30% in the ejaculate. Take 30% of the ejaculate and let's see. Somebody should do that for me. 30% of 259. Quick. We have to be fast, and you have to understand it too. 30% of the yes, 30% of 259, what it is?
77.7.
This is 77.7 million. This 77 is more than enough to say that that person is normal. Is that not it? Good. If you have somebody who has 15, remember 15 is now is the minimum. Even though people are still quoting what do you call it, 20 million, but now WHO standard puts the minimum level to 15. So let's even take it like the person should even have 20 million, and he loses the first portion of the listing, and that means that that person will be left with what? 20 million. He loses, actually he has 20 million per male, and that person loses the first portion. Also, now get me the percentage of such a person, so that he'll be left with just 30%. I hope you are. I'm going to drive out something. He loses the first. He loses the first. The first portion, which is 70%. He'll be left with 30% of the 20, and he'll be what will be the count? Yeah, the person who helped me with the first one. What will be the count? The person who actually has 20 million. And by all indications, 20 million is a normal count. He loses the first portion and now goes into have the specimen delivered for count. And then you do it. The person will be left with 30%. and that 30% will just give you 6 million. And you say that that person is acute oligospermia, as you may want it. You see that, but this person is normal. Okay, so because of the huge range in the normal count, if you make errors, sometimes you are not able to pick the error. So if somebody has a range which is close to the lower limit, that person usually have a disadvantage, because any mistake in there will draw that person to oligospermia. You understand? So you must be very careful about that. Right. So sperm count traditionally is being performed manually. Okay, manually using a hemocytometer. And I'm sure that, and I keep on saying that it's so unfortunate that these days, because of the auto analysis, somebody may not even have seen a hemocytometer before. All right. And I'll not be surprised if somebody hasn't seen a hemocytometer before. All right. So, but anybody who has gone through a lab program will have a fair knowledge about the hemocytometer, which we call the counting chamber. All right. And then hemo means a blood. All right. Cyto means cells. Meter means measurement. So this is just a small equipment which is used for the measurement of blood cells, as simple as that. However, there's also a specific chamber, all right, which has been specifically designed to count sperms. So now we are saying that, for example, if you have to do counting chambers, that will also take us another course altogether. There are various types of counting chambers. And even though the hemocytometer, the improved neighbor counting chamber you're going to talk about, which is used for most of the counts, including CSF. But who can tell me the specific chamber which is designed for CSF count? Who can tell me? This is the last day. Whoever tells me, I'll put down some 10 marks for you. A cytometer, or for that matter, a counting chamber, which is designed specifically for counting cells in CSF. Okay, so for want of time, it's fixed Rosenthal.
Improved.
No. It's fixed. I'm saying that, yes, the improved counting chamber, improved neighbor counting chamber can be used for anything, okay? Can be used for anything. But I'm saying that if you are dealing with counting chambers, there are certain chambers which have been designed specifically for certain measurements. And that's why we're going to introduce the macula chamber. Macula chamber is also a chamber, but this chamber has been designed specifically for counting sperms. And then I'm saying that, yes, you can use the hemocytometer as a what do you call it? I mean, I can't say, the hemocytometer can be used for counting any cell. But I'm saying that for your knowledge, there is a chamber which is designed specifically for counting cells in CSF, for example. And that's called fixed Rosenthal counting chamber. Fixed as in FUCH''S. Fixed Rosenthal. Of course, I'm sure you can spell Rosenthal. ROSENTHAL. Rosenthal counting chamber. Fixed Rosenthal counting chamber is designed specifically for CSF. And like I'm saying, if I want to deal with counting chambers, it's also another broad topic altogether. But for avoidance of time and all those sort of things, we just keep it at that. At least I've mentioned fixed Rosenthal. They are also going to mention that there's also a chamber which is called a macula chamber, macula counting chamber, which is also designed specifically for the count of sperms. All right. Now, because we want to be very proficient in semen and all kind of things, I'll take my time to take you through the macula, because if you go elsewhere, nobody uses neighbor counting chamber any longer. If you go anywhere outside the country, nobody uses the improved neighbor counting. However, you are still using the improved neighbor counting chamber. So I'll take you through both. Since the macula is new to almost all of you, then you start with the macula and deal with it so that even if we are unable to deal with the improved neighbor cantigema, we can just skip through and then you take it like that. But the macula is a new area, and as students of andrology, and for that matter, semenology, you have to know something that the ordinary person doesn't know. Okay? Everybody knows about the what do you call it? The improved counting chamber, the improved neighbor counting chamber. Everybody knows about it, but most people don't know about macula. All right. So this is a picture of the macula counting chamber. It is designed specifically for sperm counting. And look here. Look here. This is 0.01 square millimeters. Okay, 0.01 square millimeters. Take note. So wherever you're seeing a square millimeter, what comes into your mind?
Area.
An area. There's an area in all chambers. We have grids, what we call grids. Grids are lines, which have been drawn in a manner that will give you a specific area to count. Okay, and they are normally in squares. So wherever you have a grid, and so with this one, there's a grid. But look at this picture and look at this picture. This is the base. Okay, now this one too. This is the big. This one is the base. Now this is a cover slip. The one covering here, this one is a cover slip. This one is a cover slip. And you realize that with the ordinary counting chambers, the grid is on the chamber itself. The ruling, the lines which create the squares are on the block itself. All right. However, with the macula chamber, the ruling is on the cover slip. And put it, it's on this one cover slip. I'm going to, as we move along, you're going to see them separately. And look here, you will see that they have 4 pins here. And take note of them. You discuss them. These 4 pins, very, very important. All right. And there's a hole here, hole here. This hole here and hole here will give you a guide when you are placing the cover slip on top of the chamber. It will guide you, okay? Because there's another point here, there's another point here, which will guide you so that you don't turn the hole here to this point, for example. It will dislodge the whole thing. Once you're able to locate these 2 holes, as soon as you place them in, they will fit onto the 4 pins here. And the 4 pins here have been made in such a way that they keep this cover slip suspended. Not suspended as in say there's a floating, no, but it creates a space. You see, whenever you have a chamber and a cover slip, there is always a space between the cover slip and then the main chamber. I hope that you are following it. Just like when you have an ordinary wet mount. All right. You have the microscope there, microscope slide there. You have your drop of suspension or whatever fluid, and then you put the cover slip on it. There's always going to be a space between the cover slip and then the slide. Remember when we try to calculate the depth of a wet preparation, when you put on a drop and then you apply a 22 by 22 cover slip, you know that you can calculate the depth of the chamber there. So this one, because you're going to use it for count, then the space there should be fixed. And this pillar makes sure that once you put the cover slip on it, it doesn't allow you to go further or above it. And so this pillar will give you the depth of the chamber. And the depth of the chamber is what you have here. And what is it? The depth of the chamber here is what?
10 microliters.
10 microliters. Now, and this is what you have to do. this whenever you are going to, this is supposed to be a square, okay? And then this is going to be a depth. So if you multiply, and this is an area, if you multiply an area by a depth, what are you going to get?
Volume.
You have an area, and this is a depth. What are you going to get? Somebody said it's correct. You're going to get a volume. Good. Volume. So you see, because measurements are going to be counted, cells are going to be counted within specific volumes. So you should know this is where the whole thing is coming from. So you have an area which is 0.01, and then we are going to go through how we got this 0.01. You're going to, I'm going to take you there. This is 0.01. And then this one is 10 micrometers. But the trick is that you can't multiply, when you're doing multiplication, the units must also conform. Is that not it? When you are multiplying, the units must conform. So this is square millimeters, and this is a micrometer. So what must you do? Please be fast, be fast. We have a lot to learn today, but I don't want to rush through without you understanding them. I'm saying that if you are going to do multiplications, then the units, once you multiply the figure, the units too must be multiplied. Is that not it? Otherwise, you wouldn't get square millimeter. So it means that this was one side was millimeter, and that side was millimeter, and that's how come you got the square millimeter. Okay, but if you are going to get a volume, then there should be area multiplied by the depth. The depth is in micrometers. So what must you do, please? You must also convert the micrometer here also to millimeters. Okay, otherwise you can't multiply. If you want to calculate the volume under this, you can't do it because this one is in micrometers and this one is millimeters. How can you multiply? So there should be that kind of correlation between the units. So the 10 micrometer, which is a depth here, should be converted to millimeters. If you convert 10 micrometers to millimeters, what will you get, please? Somebody, quick. 10 micrometers to millimeters. Hello, please. This is JHSO.
They divide by 1,000.
You divide by 1,000, what are you going to get?
0.01.
Yes, so 0.01. So this is a 0.01. The depth here is 0.01. So in future, when you're going to do a calculation, remember this one, that the depth for this chamber is 0.01. And they have written this one here to tell you the depth. And they have written this one here to tell you also the area. When you go to the normal counting chamber, the improved neighbor counting chamber, you see some of these figures there, and people don't know what they stand for. So I'm just telling you that this is the smallest area under the chamber, and this is also the depth under the chamber, so that you can always multiply and get a certain volume. All right. So we are trying to look at the chamber unit by unit. Let's go back. You see that when you look at this, okay, this side look rounded. Is that not it? It is rounded, but you have the block here. So sometimes if you put it under the microscope, because this side is rounded, okay, because this side is rounded, it doesn't fit well under the, you know that under the microscope, the stage, you have the clips. You can appreciate the clips under the microscope, under the stage. Now, the clip is unable to grasp this block very well because this side is rounded. It's unable to grasp it very well. And so in the counting, there can be some kind of disturbance. All right. So you will have here what you call the chamber grip. The chamber grip is also there available for you, so that once you have your chamber here, you can put on the grip here, so that the grip will now give it that kind of rectangular shape. Hello, you haven't seen some before. And probably this is the only reason why probably you may have to be practical, so that you can get a feel of a macro chamber. And then in future, if you want to buy some or if you want to use it, you can use it. Otherwise, all the things that we are going to do, we don't need physical presence. All right. But since some of you may not have seen a macro chamber before, probably that might be the only reason why you may have to meet. But I'm taking you through, and even when we have to meet, or if you don't meet, you will be able to handle it. So the chamber, as you saw up here, I'm saying that for it to be able to fit very well fixed under the microscope, there is a grip. There is a grip, and this grip can be used to fit in, so that once you put this one into the grip here, this is already a rectangular. And you know that under the microscope, all right, the slide is already a rectangular. And so that's how come the, what do you call it, the stage clips can grasp it and make it firm. So that is the chamber grip. So it's movable. You may use it or may not use it, but it's always good to use it. All right. And then after this is the cover glass. It's not the normal cover glass. This cover glass has the grade, the ruling, the lines, they are on this one. Okay. And this is the base. So the big difference, what makes it interesting here is that unlike the normal counting chamber, where you put the cover slip first and then try to now squeeze the suspension or fluid in between, and then the fluid will now move by capillarity. Okay, I'm hoping that all of you may have had an experience with how to put or charge a chamber before. And you know that when you want to charge a chamber, you have to apply your cover slip first. Once you have applied the cover slip, you now push the sample between the small space between the chamber and then the cover slip. All right. Here, this space here is what we're going to take the specimen. So it means that you can conveniently take put the specimen here before now you come to apply the cover slip. So that makes it easier, unlike the other one. Okay. Now, so the in between here has the has the space for your sample, and then once you put the cover slip on it, remember the 4 pins there. So the 4 pins will now give you the kind of depth, so that once you put the cover slip there, in between this base and then this thing is fixed. You can't go beyond it, and that is the 0.01 millimeter depth that we talked about. And then there's also some accessories. There is this brush. The brush, if you have a new chamber, you to always come along with a brush. The brush, this thing is said that you can't use your finger to clean it. So you have a brush, a small brush there. You take it with water. You put this side in the water a little bit, and then you just use it to clean the inside. And the same thing, use the brush also to clean the top of the glass, and that's it. You don't want you to use some gauze or something to try to clean this one. All right, good. And then there's usually what do you call it? Some small stick, which you may not need. The stick is what people use to, if the specimen is here, okay, if the specimen is in a cup here, you put the stick, you take a drop of the listing and then put it in the middle here. That's all. That's all. But this one may not even be needed. You can just use any pipette or something to take a drop and put it in the middle here. Okay. So that's the macula. So same, I think I've talked a lot about the chamber grip, just to give it a grip and then makes it comfortable. This is also the cover glass. Okay. So the cover glass has some rulings. Now, the first square, or the square the main square on the this thing is 1 millimeter. When you say 1 millimeter, it means that 1 millimeter length, 1 millimeter width, and once the square, it means 1 millimeter each way. And then the square, which is 1 millimeter square, will now be divided into 100. So if it has to be divided into 100 smaller squares, then what does it mean? Each side, how long is each side? I think I put on a platform that we are going to do some calculations. Please try to move along with me and understand it. You have a square, which is 1 millimeter square. And we want to now divide this 1 millimeter square area into 100 smaller squares. So if you want to do that, technically, what will you do? One side is 1 millimeter, the other side is 1 millimeter. Which is 1 millimeter square. You want to divide that one square millimeter area into 100 smaller squares. What will one side, the division for one side, what will it be? If you don't understand some of these things,
0.1.
0.01.
No, you see, the first thing is that it means that the side, one side should be divided into 10 sections. That's the way to go. It's 1 millimeter. You want to get 100. It means that you must divide one side into 10 sections, and the other side also into how many sections?
10. So it's 0.1 times 100.
So you see that once you divide this side to 10, you divide the side to 10. Once you cross each other, you are going to get your 100 squares. So once that has happened, then it means that one side of each smaller square is the 1 millimeter divided by 10, because this one millimeter has now been sectioned into 10. So it means that one small square has a side of 0.1. Okay, so if one side has 0.1, then what is its other side?
0.1.
0.1. So what will be the square then? For that smaller square, what will be the square? What will be the square?
0.01.
0.0. So this is the 0.01. This is the one that you saw out here. This is the 0.01 that you saw here. Okay, so we are not just looking at the numbers. We want you to appreciate it so that it's not like the numbers are there for being their sake. So it tells you that once you have area which is 1 millimeter square, and now it's been divided into 100 squares, what it means is that one side has been divided into 10 sections, and the other side too has been divided into 10 sections. Once you have the 10 here, and then you crisscross, you are going to get 100 squares. Once you get 100 squares, you'll be able to calculate the area of each small square, and that's what you have just done. And so now you have you now understand the 0.01 millimeter square. Okay, you now understand it. Is that not it? Is that not
Yes,
it?
please. Yes, please.
Yes, please.
Now you know that the depth, when you put on the cover slip, the depth is what? The depth is what?
10
10
micrometers.
micrometers.
10 micrometers. And when you also convert this one into millimeters, what will it be?
0.01.
0.01. So therefore, it means that you can calculate the volume which is captured by each small square. Is that not it? You can do that because each small square, you know the area, and then you also know the depth. So once you put a certain volume in there, the volume which is captured by each small square can be calculated, and that is the 0. The area which is the 0.01 millimeter square multiplied by what?
The depth, which is 0.01.
The 0.01. So you can calculate the volume. You can calculate the volume easily. Can somebody help me with that? Can somebody help me with that? Please, let's move quick.
This is 0.0001.
0.0001. Fantastic. So if you know this one, it will be very easy to move on to the next section. Now, so you realize that the macro chamber has been made in such a way that if you count 10 squares, you'll be able to get one. Let's get there so that you don't get confused. So this is the brush. I've talked about the brush and what it is used for. This is just a tissue paper. Sometimes we're just talking about the things that you may need if you want to do if you want to use the macro chamber for your counting. And you require a tissue, not toilet tissue, of course, the tissue, the laboratory tissue. And then that is what you don't want you to be using your fingers, because if you use the fingers, any small dirt that gets itself attached to the grid will also create some kind of particles that can be confused in the counting. Okay, all right. So the macro chamber, like I've said, it has the lower base. It also has the upper glass. The upper glass is the cover slip that you know. And then we said that the chamber inside the depth is 10 micrometers. And I want you to be able to convert the 10 micrometers to millimeters, because the whole thing has been, the sizes is all in millimeters. So if the size is in millimeters, the depth you also in millimeters, so that it will afford you the opportunity to do your calculation and get your volume. Okay. Now, once you set it up, okay, once you set it up, then you recommend that you use 20 times 20 objective. The reason is that the times 10, all right, let me also go back again. If you are using a microscope and then it is in focus, as soon as you focus, you see that the objective, between the objective and then the slide, if you're using ordinary slide, cover microscope slide, there's a space there, is that not it? That space is called the working distance. All right. Now, the higher the objective lens, okay, the higher the objective, the lower the working distance. Do you know that already?
Yes, please.
Yes. The higher the magnification, the lower the working distance. Now, if you look at this whole thing, you see that's a big block. Okay. Now, if you want to use times 40, you can't focus, because times 40, the working distance for times 40 is lower. And then the block too is a big thing. So that times 40 will hit it, will hit the block, and then you can't focus. Times 10 will give you the times 10 is okay. It has a bigger working distance to be able to accommodate the macular chamber, which is a big block. However, the cells may be too scanty, not scanty, maybe too small for the count. You may not be able to see the cells very well to do the counting. Okay, so the appropriate, convenient magnification is the times 20. Unfortunately, most of us in our labs, we don't use the times 4. We also don't use the times 20. So most people, once the microscope comes, they take away the times 20. They also take away the times 4. So you realize that there becomes a challenge as to how you'll be able to have the times 20. If you want to do proper semen analysis and you are fortunate to get a macular chamber, then it means that your microscope should be one which is fitted with times 20, because that's the most convenient objective lens that can be used appropriately to do your counting under a macular chamber. Now I'm saying so because the macular chamber is a bigger block. And once a bigger block, it makes it difficult to use the times 40, which has a lower or smaller working distance. Ladies and gentlemen, are you following the discussion?
Yes, please.
Okay. So that is that. All right. So the macro chamber, very, it's easy to use. It gives fast results. A fast result to the extent that you are not going to do any counting. Now I'll take you to where we have our what do you call it? The grade, and once you see the grade, it gives you 100 smaller squares. Now, if you get 100 smaller squares in the what do you call it? In the macla, you are not going to do any dilution, as we have with the counting. The neighbor counting chamber. Remember the neighbor counting chamber. You are going to charge the chamber, and so once you are going to charge the chamber, and then by capillarity, if the specimen is viscous and you don't dilute it, you are not able to. You can't count. Okay, you can't do that, and so it will be necessary. I mean, it's a prerequisite that you have to dilute. Now, with this one, you are going to apply the sample straight away and then use the cover slip just to cover it. And so there won't be any issue about capillarity. Okay, so the specimen is just put a drop is put in there, a cover slip is just applied, and that is it. And so it makes it very simple. So elsewhere, you use the preparation in the chamber to assess even the motility. You are going to use it even to assess your morphology as much as possible, because here, remember that we said that if you do a wet mount, you put a slide, you put the cover slip on a wet mount. What is the depth? Do you remember the depth when you did the calculation? You said you're going to get about
0.01.
You are going to get 20 micrometers. You don't remember. When you have when we were talking about the wet mount preparation, we said that if you have a 22 by 22 and you put on a 10 microliter aliquot there, you do the calculation, you're going to get 20 microliters. You have forgotten that one. Now, that 20 microliters, also before I come to that, if you are doing any wet mount and then you focus, do you realize that you keep on turning the fan adjustment even as you move the slide? You keep on turning the fan adjustment. Do you do that all the time?
Yeah.
Yes, please.
Or stool or whatever, any wet mount, do you keep on turning the fan adjustment?
Yes, please.
Okay. Why do you do
Yes,
that?
please.
Why do you do that?
To sharpen the image.
No, that is okay. So what again?
To also bring the image to view or the morphology, it will give a clear morphology.
Right. That is very primary. But you see, the thing is that you know that once you are in focus, you are at a certain focal point. Is that not it? When you say you are in focus, if you are a focal point, is that not it? And if that focal point gives you a plane, a focal plane. All right. So it means that anything above or below that plane, you can also see it. Okay. So since you have a suspension, and for this particular, the one that we talked about, let's say you are going to get a depth of 20 micrometers between the cover slip and then the slide. You have that space about 20 micrometers. But the microscope will give you one plane at a time. So the object of keeping on turning the cover slip, this thing is that you are only seeing what is in one plane. So as you turn it, you're also going to see what is at another plane. Okay, so you keep on turning it, and so because I don't know, these are very, 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 very practical things that, and as scientists, like I've said, keep on saying that the thing that we do, everything, anything that you do, you must have the science behind it. Okay, otherwise you'll be an ordinary person who has been trained on the bench. All right. So the science is that once you are in focus, you are just at a certain focal point and gives you a certain focal plane. So anything along that line, that plane, you see it. But anything below it or above, you can see it. And since it's a wet mount, there's possibility of some of the elements or the cells or whatever you want to see, they will never all lie on this one plane. They will never all lie in one plane. So some will lie in one plane, this plane. Then the next plane down, there's also another set of cells. The next plane down, there's also another set of cells. So in keeping on changing the focal change, it means that you are changing the focal planes so that you'll be able to see the things at each level. That is what it is. Right. So if you watch this particular one, you see that the space, the depth is just 10 micrometers. Is that not it? It's 10 micrometers. If we look at the normal neighbor counting chamber, I'm sure all of you have seen the neighbor counting chamber. We use it. What is the depth of the counting chamber? The depth
0.1.
0.1. 0.1 in micrometers. What is it? Zero 0.1 in micrometers. What is it? Zero 0.1 in micrometers. What is it? It is 100 micrometers. Okay, the depth of the noble counting chamber is 0.1 millimeters. 0.1 millimeters is 100 micrometers. Look at this one. This one is 10 micrometers. So this is a tenth of the space that's allowed. Okay, so it means that you can have the sperm cell lying in just one plane, as opposed to the one you have with the neighbor counting chamber, which is 100 micrometers. It means that you can have levels. 100 micrometers can give you up to about 10 levels, so that you can have cells lying in. So this gives you just one plane, and this one plane will now allow the sperms, if you want to see sperms movement. This is just one plane, so that you see the movement in one plane, and now you can do a better evaluation. You see the trick there. So the depth here, the 10 micrometers, is giving you a tenth of what you have with the ordinary neighbor counting chamber. And that means that in the ordinary neighbor counting chamber, you have a lot of levels. And so you can have a cell line here. If you don't keep on turning your what do you call it, your fine adjustment, if you don't keep on turning it and you just focus it and then count the cells there, you miss a lot of cells, because the cell that you are counting is the cell that is at that level, at that plane. What about the cells in the other plane? You see? And so that is, I want you to appreciate the science behind everything that you do. So the one big advantage of the macro chamber is that it gives you one plane. You have only 10 micrometers to maneuver, and therefore you can't have two cells lying one up here and one down there. And so if there's also a movement, every cell will now move independently, and now you can assess its movement very well. And then that also will also allow you to what do you call it? If there's a progression, if you want to assess your progression, all of it is the macro that can afford you to now do a proper evaluation of the sperm movement, because now everybody is lying on just one plane, and there's no distortion for any other. So if they are all moving in one way, you know that they are moving in one way, and that gives you a better evaluation, as opposed to the initial wetman that we are using to do the what do you call it, the evaluation. Okay, so that is that. So the only problem here is that now this macula chamber, you don't dilute the cells. Sorry, you are not going to dilute. Okay, it means that the cells will still be moving because you didn't add any diluent. It's the diluent which kills the sperms. So you are not going to do any. So two things that you do to immobilize the cells. Either so you use the what do you call it? The preparation, the first preparation to assess your movement and everything. And then after that, you put the the slide, the chamber on a warmer and place it around 50 to 60 degrees. If you put the warmer around 50 to 60 degrees, what will that? You kill all the sperms. And so now the sperms are immobilized, and then you bring it back onto the chamber, and then you begin to count. All right, because if the cells are not killed, I mean, and they are still moving, when you're doing the counting, I mean, you see that you may be counting one cell 3 or 4 times because the same sperm will go here, come back, and then so you have to do that. Or if you have done your assessment already, then what you have to do that you immobilize the specimen, the same specimen, just put it in the test tube, put it at 50 to 60 degrees, and then kill them. Okay, once they have been killed, now you can take a mix and take a drop, put it in the middle of the macula chamber, apply your cover slip, and then there you go, you do your counting. Now, here we are going to go forward, and then so all these things, I've talked about all these things, so don't worry. And then here, the fact that you can put the specimen on 50 degrees and so forth, 50 to 60 degrees. If you don't have a plate, a water bath, or anything that can give you 50 degrees, then remember that when we're dealing with the diluting fluid, I said that if you don't have a diluting fluid, you are going to use just ordinary tap water, okay? Or the still water, let me put it away, and it can work for you. That is in there. Similarly, if you don't have a means of getting a 50 to 60 degrees water bath, what you do is that you boil water. When you boil water, of course, water will boil at 100 degrees. Is that not it? Now, if you take 2 cups of water or whatever volume, 2 volumes of that boiling water, you take 2, you add 1 part of ordinary tap water. It reduces it to 50 to 60 degrees. You can try that in your lab and see. So allow the water to boil. And I'm saying, when I say 2 cups, it does not necessarily mean 2 cups. It's say 2 parts. So that 2 parts, you can, if you have some whatever that you are using to fetch the water, fetch two times of that, and then fetch another tap, 1 part of water, add it to it. Take your temperature. It will never go below 50 degrees or above 60 degrees. You'll get your distance, and use that one to immobilize your sperms. Okay, all right. So I've skipped the calculation of this one because I have a full slide on that. That's why, otherwise you may get confused. So the macula, you use undiluted immobilized semen, and I've told you how you are going to get the immobilized. Either you charge the chamber and then you put it on not on a water bath, but on a warm plate at 50 to 60 degrees. They will kill all the sperms while it's still in the chamber. Okay, or you will do what I've just told you. Put the specimen in the 60 degrees, 50 to 60 degrees environment. All right. And I've told you, if you don't have a proper control, you can use this crude method. Then you do that. Once the sperms are dead, you can now go ahead and charge. All right. So this is what I was. So this is just the process. So this is your chamber. The middle here, you can just take a stick or you can take a drop or anything. Just take a drop into the middle here. Okay, that's where this thing is. And then this is your cover slip. Remember, I've told you these 2 pins here. They are not the pins, they are the holes. So they will fit into some holes here to guide you. As soon as you do that, this whole thing will sit on this 4 pins. Once it fits the 4 pins have been designed to give you a depth of 10 micrometers. And that's all. So this one will now give you that kind of space to do your counting. Very, very, very simple and easy. So all these things, the steps, I've mentioned it already. So once you are done, you're allowed to settle. Of course, for any movement, any suspension that you make, you have to give it about a minute or 2 for the cells to settle. And then after that, you put it on your cover slip. And then we recommend that you use 20 times 20 objective. And I've explained why you are using the times 20 objective. That the working distance between this is the working distance. The working distance between the objective and then the slide. This is a huge block. All right. If you are going to use the times 10, fine. The times 10 will give you a big working distance, a big space. But the cells that you will see will be too tiny. If you are going to use the times 40 will hit this one and you can't get it. So times 40, so times 20 is better. Now, look, this is the ruling or the grade under the chamber. So you have the entire square is 1 millimeter square, 1 millimeter here, 1 millimeter here. So that will give you 1 millimeter square. And then you want to divide it into 100. So if you want to divide it into 100, all is to divide this side by 10 and divide this side also by 10. If you divide this side by 10, which is 1 millimeter, it means that you can get the size for this one. And that's the 1 millimeter divided by 10. That's going to give you 0.1 millimeter. As simple as that. Once it is a square, and this side is 0.1 millimeter, this side is also going to be another 0.1 millimeter. Now, so you are going to get 0.01 millimeter square. Now, so that is the area under the chamber. Okay. Now the depth is already established as 10 micrometers, which is 0.01, 0.01. All right. So you can calculate and get the volume here. You can equally get the volume on the entire square area. Okay. You can. Now it is recommended that you count 10 squares. This is 100. Okay, this is 100. And 10 here is 100. Any 10 squares. So either 10 here or 10 this way or 10 this way. Any 10 squares. Once you count 10 squares, it gives you 1 micrometer. 1 micrometer. You are going to do the calculation and you see it. It gives you, so you are going to get the number of cells, the number of cells per micrometer. Okay, and the 10 per micrometer, if you use 10 of them, then the 10 is going to give you any number of cells that you get. If I can, for example, let's take the first 10. So the cells here 1, 2, 3, 4, 5, 6. Okay. So as soon as I get my 6 million per mil, I will take you through the calculation. It is very interesting. So let's say if we want to go this way, it's going to be 1, 2, 3, 4, 5, 6. There's what we call the borderline rule. The borderline rule is saying that this square, any square here has 4 sides. All right. If you have a cell lying on 2 sides, So you yourself can choose two sides. Either this side and this side are included, and this one side and this side are excluded. Okay, I'll take you through all of that. So when you have any square and you are counting cells, the borderline rule is saying that for the 4 sides, take any 2 of them and cells that are lying on those 2 cells, add them to it. And then cells that are lying on the other 2 sides, we'll also take them out. Okay, I'll take you through all of that. And then that's the principle that we use. That's the principle that we use. If you don't do that, for example, if you have a cell here, okay, and then you don't apply that rule, this cell may be counted as part of this square. And once you also come here, this same cell can also be counted as part of this very square. So it means that this cell is being counted twice. But if you rule 2 sides in and 2 sides out, you see that that rule will allow you to count this one only once. Okay, all right. So just have a good appreciation of the squares here. All right, and see how you are going to go on with the calculation. It's very, very simple. Good. In the event the number of sperm is substantial, count their number in strip of 10 squares. If it is right, let me go back again. So the cells are substantial. You are allowed to count 10. What do you call it? 10 of the smaller squares. The cells in the 10 squares, any 10 squares, and ask your answer. Or if the cells are not too much, you are supposed to count all of them. When you count all of them, how are you going to get back to the original result? You are supposed to count 10 squares, 10 cells in 10 squares to get your result. If you decide to count everything here, what must you do to your new value to get to get back to the result?
Papa, please, you divide by 10. You divide the 100 by 10 to get your result.
How you get your results. So you, as you move along, you see that you're saying that if you count any cells in any 10, the number of sperm that you get, if it's 1, 2, 3, 4, 5, 6, the value is 6 million per mil. Straight away, 6 million per mil. Okay, now I'll take you through and you understand how you get the 6 million per mil. So, but the value is that if you count the 10 squares under the grid, any number that you get, if you get 20, if you get 100 or whatever, just add million per mil. If you get 55 in 10 squares, it's 55 million per mil. Now, if the cells are scanty as you have here, you are advised to count everything here. If you count everything here and you also got 55, then for your result, you must divide your 55 by 10 and you get 5.5. Then the result gives you 5.5 million per mil. All right. So this is it's all good. So noting that the errors associated with counting smaller numbers, blah blah. I've said that. Okay. So this is the macula from the addition of the addition of the sample to the covering of quartz slip application. This is just a summary, and you have your counting in this way, and then you can decide to count any 10 squares as the case may be. All right. So, and remember that you have you are going to use a microscope, and a microscope will give you a field of view. You know a FOV, a field of view. Every microscope will give you a round field of view, and you know that the higher the magnification, what is its influence on the field of view? The higher the magnification. The higher the magnification, what is its effect on the field of view?
The smaller the field of view.
Fantastic. The smaller the field of view. So if you have a 10, this in here, like this one, this is so, but you are counting 10 cells, so you should know, so that you don't but I'm not getting the entire list. How can you get the entire thing when you are using a microscope that gives you a round field of view? So, but you know that you are counting 10 fields, so you can decide if there's 1, 2, 3, 4, 5, 6, 7, any 10 cells at all, then you are there. I'm still going to have to take my time to take you through the counting. Sorry, the calculation. The calculation, let's come back to the fundamentals. Coming back to the fundamentals, we're saying that now we know that each side of this small square is what? 0.1, okay? Now the side here is also 0.1. So we are going to get an area of 0.01 millimeter squared. And you have a depth of also another 0.01 millimeter. Do you all agree on that? Hello? Hey, ladies and gentlemen. Hello?
Hello.
Hey, virtually I finished with the macula, but I want us to now take our time to get why do you say that if you count the number of sperms in 10 squares, you just add million per mil. I want us to take through the mathematically so that you can appreciate it. And we are saying that from the basis, we know that the smaller square, each side is 0.1, and we all of us appreciate why it is 0.1. And once this is 0.1, this side also 0.1. So it gives you an area of 0.01. We appreciate that. Is that all right?
Yes, please.
Okay. And then we know that the depth too is standardized. The depth is 10 microliters. Sorry, 10 micrometers. And the 10 micrometers is 0.01. Okay. The 10 micrometers is also 0.01. Good. Now, the depth multiplied by the area will give us what? The volume. What will be the volume here? The volume here. What will be the volume? Please, somebody help me.
0.01.
No, the volume is not 0.01.
Sorry.
The volume.
0.0001. Yeah, 3 zeros.
Not 3 zeros.
I mean,
Is it 3 zeros?
yeah, 0.001.
0.001.
Let me
0.001.
0001.
0.01. Okay, so you have 3 zeros. So 0.0001. Millimeter what?
Yeah.
Millimeter what?
Cube.
Millimeter cube. Okay, millimeter cube. Very, very good. So if you count 10 of the squares, if you take 10 of the squares, what total volume will you be using? If you take 10 of the cells, remember we said that so each small volume will give you us the 0.0001 millimeter cube. If you are counting 10 of the cells of the squares, what total volume will you have?
0.001.
Very good. 0.001 what?
Millimeter cube.
Very good. Now, millimeter cube is the same thing as microliter. You know that already.
Yes, please.
Do you know that? Do you know that? Millimeter cube
Yes,
is
please.
equivalent to 1 microliter. You know that?
Yes, please.
This is not one person. I want all of us to appreciate it. Millimeter cube is the same thing as microliter. So therefore, the volume for 10 squares is going to give us 0.001 microliter. Is that all right?
Yes,
Is that all
please.
right?
Yes,
Good.
please.
Good. Now, the 0.01 microliter Now, if we have, let's say, for the 10 cells, we have n number of cells. Okay, if you have n number of cells, n number of cells for the 10, what will be our calculation now? So the calculation will be n in 0.001 microliter. Is that not it?
Yes,
Please
please.
take your pens and papers and make sure that you understand this one. So that the number of cells in the 10 smaller squares is equivalent to n in 0.001 microliter. Is that all right?
Sure.
Good. So E means what? Mathematically, E is what? If you say 1 in 2, what is it? Is it not 1 over 2? If you say 1 in 2. So if you say n in, hello? If you say 1 in 2 or 1 in 4, mathematically it's 1 over 4. Is that not it?
Yes, please.
So if you say n number of cells in 0.001 microliter, then it means it's the same thing as n over 0.001 microliter. Is that also correct?
Yes, it's correct.
Good.
It's like a ratio.
Good, very good. So this is a ratio. So the 0.001 microliter, is it not the same thing as
N is
the 0.001? If you make it a fraction, what is it?
One over 1,000.
1 over 1,000.
1,000.
1 over 1,000. Good. So it is n over 1 over 1,000 and then the microliter. Do you see that one? Please take a pen and paper. So
Yes.
if you have A over B over C, how do you express it? A over B over C. How do you express it? Is it not A over B times C? Is that also correct?
Yes, please.
Is that also correct?
Yes, grandpa.
A times C over B. Yeah.
If A over B over C is the same thing as A over B times C, then it means that n over 1 over 1,000 is also the same thing as n times 1,000 over the 1. Is that also correct?
Yes.
Yes.
Yes, grandpa.
Good, good. So it means that the number of cells multiplied by 1,000, okay, is per microliter. Is that all right? Now we want to we know that we report sperms in per mil. Is that not it?
Yes, please.
You know that we report sperms in per mil. Is that not it?
Yes, please.
So now the answer that you have gotten, what is it? Is it in per mil? The calculation that we have gotten, our answer, is it per mil?
No, please.
It's per microliter. Is that all right?
Yes, please.
Yeah.
So we have to convert the microliter also to mil. Now to convert a microliter to mil, what do you do? You also divide by 1,000. Is that not it?
Yes, sir.
Now you realize that the microliter is per sorry. If you have it per microliter and you want to convert the microliter to mils, so that's also going to be 1 divided by 1,000 to convert the microliter to mil. So to divide it by 1,000, it means that you also have to rather multiply it by, as we did for the first one, you have to multiply it by 1,000 again. Is that not it?
Yeah.
I hope you are not confused. We are converting the, we have gotten n times 1,000 per microliter. We want to make our report in per mil, not per microliter. So we must convert the microliter to mils. To convert a microliter to mil, we divide by 1,000. So to divide by 1,000 means 1 over 1,000. So the 1 over 1,000 at the numerator side will now have to make the 1,000 multiply up. So we are going to get n times, we already have 1,000 there, multiply by another 1,000. Is that not it?
Yes.
You convert the whole thing, now the whole thing becomes per what?
Mil.
Mil.
Okay. How many thousands we have? We have 2,000, 1,000, 1,000, 1,000. If you have 1,000, 1,000, what value is it?
1 million.
A
1
million.
million.
So now you get n times 1 million per mil. Is that not it?
Yes.
Yes, please.
So what then the convention now will tell you that if you count n number of cells, just add million per mil. Do you now appreciate it?
Yes, sir.
Good. So the macla is just makes you to avoid any calculation. But even once you are avoiding the calculation, you must understand the principle behind that calculation, so that you don't say, "Oh, after macla, you just count 10. You take 10 squares, count the number of cells there, and then add million per mil." That is correct, but it is coming from somewhere, and as scientists, you must know the basis of that of where it is coming from. And I'm hoping that those of you who are listening, I'm sure you have followed it. Then you can do your own practice and make sure that you grasp it very well. And so that is it. So the number of cells, if you counted 10 squares and you had 13, it is 13 million per minute. That's all. 13 million per minute. If you counted number of sperms, let's say 100 in 10 squares, and you had 100 sperms in 10 squares, it is 100 million per minute. That's all. A million, remember, million is times 10 to the power 6. So whatever you are getting, either you write n times 10 to the power 6 per mil, or you write n million per mil. That's all. And that is the mathematics behind the macla. All right. I'm sure that once you take your time to, unfortunately, the slide here did not take this nitty-gritty as part of my slide. And so if you want to follow it, you have to go back to your own basis in mathematics and then do that. All right. So now you are done with that one. And you know that that is a new area. And so once you are done with that, we are almost done. So as for improved neighbor cavity chamber, it's very simple. But also will involve calculations just similar to what we've just done. Okay. So most people will use the improved neighbor cavity chamber, all right? And then this procedure will now involve sperm immobilizing diluent. Remember, with the macla, you don't need any diluent. You don't need anything. The only, if you want to immobilize your sperms, either you put the specimen on the block, and then put the entire, you put the entire block in a warmer at 50 to 60 degrees, or you preheat the entire sample in 50 to 60 degrees, and then now pick a drop into the middle of the chamber, the macla chamber, apply a cover slip, allow some 1 or 2 minutes for it to settle, and then you count the number of cells using times 20 objective, and we have explained why you need a times 20. Choose any 10 smaller squares under the chamber and count the number of squares in the chamber. So in the 10 distance, once you are finished, any number that you get is times 10 to the power 6 or million per mil, and you are done. I think that is a very simple one. However, when it comes to the improved neighbor cavity chamber, there's going to be a use of a sperm immobilizing diluent. All right. And so it also involves loading the chamber, and then now going to use the microscope to count. And then after that, you are going to do your calculations. Okay. Now I've said over and over again now, because these days people don't use what do you call it? Manual means of doing your hematological parameters. It makes it very difficult for people even to appreciate the use of the improved neighbor cavity chamber. But the principle of the use of the neighbor cavity chamber for sperm count is the same principle for total WBC count in whole blood, and for that matter, cell counts in body fluids, including CSF. And as scientists, you should be able to do cell count from CSF. And it's the same principle. If you understand the principle of WBC count using the hemocytometer, is the same principle for the sperm count. It is the same principle for CSF count. Even some doctors may take some body fluid, some aspirate, and they want a cell count. It's the same principle. The same principle. Okay. So in the improved nearby cavity chamber, the steps are just very simple. Over there too, we have the grade. Okay, the grade. And the grade will take you through, you have what you call the 4 corner squares. So that's what we are going to use to count your distance, to count your cells. Then there's also a central square. I'll take you through that one. And then you apply the specific rules for the counting. The specific rules for the counting is what we talk about, that when you have the boundaries, for any square, you have 4 boundaries. Cells lying on 2 of the boundaries, you take them out. Cells that lie on 2 of the, you take them, you count them in, all those sort of things. So this is in brief the principle. All right. Now, like we've said already, sperm count is reported in million per male. Okay, that's how come once we got the something per microliter, you have to convert it to male, because the standard for reporting semen is in million per male. Okay. Similarly, the standard for reporting WBC is something times 10 to the power 9 per liter. All right. If you want to convert it to per male, then that will also reduce the 10 to the power 9 to what? If you want to report it per male, your 10 to the power 9 per liter will become what? Hey, someone. All right, so let's move on. So this is just a refresher that if you're doing a total WBC count, the traditional unit for measurement is something times 10 to the power 9 per liter. All right. Now, if you are doing a cell count for CSF or WBC, for that matter, WBC in the CSF or any body fluid, we report in per millimeter cube or per microliter. Remember, you know that millimeter cube is the same thing as microliter. So don't get confused. If you go to some lab and they're using the cell count in per millimeter cube, somebody is also using per microliter, is the same thing. All right, good. Now, the things that you need for your counting chamber, of course, the sample, the hemocytometer, you need a tally counter. Okay, tally counter is different from the differential counter. All right, the one that we use when we're talking about the morphology count. But a tally counter, I'll show you a picture of it. All right, and then of course you have your semen diluting fluid. We've talked extensively about the semen diluting fluid already, so we are not going to do that now. And you know, this is just a formalin, what do you call it? Sodium bicarbonate 5% and formalin 1% mixture. That's all. You change it with either crystal violet or something, and that is it. That's your semen diluting fluid. Of course, you need a disposable pasta pipette or transfer pipette. And you may need a test tube, okay? And you also need a micro pipette. That's optional. So now I'm sure all of us have seen counting chambers before, the improved neighbor counting chamber before. Now you have 2 brands or 2 types. I'm sure some of you may be confused once, or I don't know. Have you seen this tab before and this tab before? The improved counting chamber. A tab like this and a tab like this. Who has seen both before? Do you have anybody who has seen any of these types before?
Just the top one.
Just the top one, okay. You also have hello?
The top one. Yeah,
Only
number the top one.
Okay, so this is the standard one. Okay, now this is the V-shaped one. The V-load, this one, you see that it has been made in such a way that when you apply the cover slip, it has become very simple for you to load, because with this one, with the standard one, once you apply the cover slip, there's virtually no space for you even to know where to start loading the chamber. Okay, so sometimes before you could say jack, you have dispensed the your fluid to cover the cover slip, to get on top of the cover slip. Okay, it's like if you're a boy, you haven't had an intercourse before, you get a new girlfriend. Before you could say jack, you don't know where to enter. Before you could say jack, you have ejaculated into somewhere else. All right, so so that is that. So this model is the V-load type, where this gives you an easy access for loading the chamber. Is that not it? Very, very simple. So if you have the opportunity of getting this one, I'm sure that this one is better. All right. Now look here. Whether it is this one or this one, the only difference is that this one has what do you call it? You have this V-shaped cut out to help you to just move easily. But look here. What do you see here? Hello?
The area.
The area, and what is it?
0.0025 millimeters square.
Very good. Keep this one in mind. Just as you saw with the macula. All right. You know where the 0.01 millimeter square was coming from. Okay. So this 0.0025 millimeter square, you should also know where it is coming from. And now, of course, this one is the 0.100. This is 0.1 millimeter. And this 0.01 millimeter is what? The depth of the chamber. And that's why I say if you convert this 0.1 into micrometers, you are going to get 100 micrometers. That's why I said that this one, the depth here is 10 times more than the depth in the macula. Or the other way around is that the depth in the macula is 1/10 of the depth in the neighbor counting chamber. You see the difference, a huge difference. And that tells you that here, if you are doing an accounting and then you keep just one phase, you are going to miss a lot of cells, because it gives you a depth which is about 10 times this one, and therefore gives you different layers where cells could be lying at various places. All right. So this one is an inbuilt characteristics of the chamber. Now, remember I mentioned about the Fuchs-Rosenthal cavity chamber. Why did I say it is useful?
It's specific for the CSF.
Yes, sir.
Yes, very good. It has a depth of 0.2 millimeters. It has a depth of 0.2 millimeters. And that one, you see that it is giving more room, because normally cells in CSFs are scanty, unlike cells in whole blood. Okay, so because the cells are too scanty, what must you do? Do you need more volume of the specimen or less volume of the specimen?
You need more volume.
More volume. So it has been captured in such a way that since CSF naturally will have smaller numbers of the cells, if you restrict the volume, just as when we're talking about when we want to do morphology or vitality, we want you to count more cells. The more cells that you count, the higher the lower your risk, okay, or the errors. So if you have CSF, which is likely to have just scanty number of cells, and then you also reduce the volume, you will end up getting virtually nothing. So it's also designed to also accommodate a lot of cells. That's how come that one has a depth of 0.2. So once that's a 0.2 depth, if you do the calculations, you see that it can now pick more volume. And once it picks more volume, it has the chances of also pick. So these are the things that I expect you, my dear brothers and sisters scientists, to also know. Even if you are not using them, you should know why those things are there. All right. So coming back to where you are coming from, you're saying that this is the same thing. You have this 0.02 millimeter square, the same thing here. There's no difference between this one and that one. The only difference is that this has a V cutout, and this is to facilitate the loading, as simple as that. So if you have the standard one, which one? This one you must suffer to charge the chamber. With the V1, oh, just put it here, no, and you can the whole thing can now move. It's very, very simple. Okay. Now, under the chamber, any chamber for counting should have a grade. That's rulings. Now, as we saw with the macula has just 1 millimeter square, and that 1 millimeter square has been subdivided into 100 smaller squares, and then we're able to do the calculations and got it. Here, under the improved neighbor counting chamber, we have a square of 9 millimeter square. So with the 9 millimeter square, let me see if I can get. Hey, I'm trying to get my pointer, it's not coming. Hey, my pointer is not working. Okay, now let me see again. Okay, I don't know. Can you see something here? I don't know. My pointer is not showing properly. Okay, let's get it. Right. So, hey, without a pointer, will it be okay with me? I don't know. I'm not.
We see one small dot.
Small dot. I don't know why. Hey, I've missed where my pointer is. Okay, so under the neighbor chamber, it has 9 squares. It is a 9 millimeter square area, larger area. And the 9 square millimeter area means that each side here. So what will be this side? If it's a 9 millimeter square area, then it means that this side will be how many? How much? This side?
It's 3.
3 millimeters, and this side is also going to be 3 millimeters. So this entire area has now been divided into 9 squares, so that this side is 1 millimeter. This side is also going to be 1 millimeter, 1 millimeter, and 1 millimeter. Okay, so this here gives you 1 millimeter square area. The entire whole thing is 9 millimeter square. Now watch again. Since it is, you have 9 squares, 3 here and 3 here, it gives you a central square area. Is that not it? Hello, let's hurry up.
Yes, please.
So if you have nine squares, 3 here, 3 here, 3 here, 3 here, it gives you a central area, and this is what we call the central square area, the central square. And once you have this as a center, it means that you have 4 arms. So this now becomes what we call the 4 corner squares. Here, where you have the L, the L's are the 4 corner squares. Now, watch something here. You'll see that this side has been divided into 16 smaller squares here, 16 smaller squares. And that means that each side has been divided into 4 here, just as we saw with the macula. When you want to divide something into 100, then it is just 10 by each side. So this one, if you want to divide into 16, then it means that this side should be divided into what? This side should be divided into what?
4.
Follow me, let's move fast. 4 here and 4 here. Now, is it possible to calculate the length here? The size here, is it possible? Hello? Is it possible to get the value here?
Yes.
What is it? Hello? The size here, what is it? Oh, don't disappoint me. The size here, the size this side, what is it?
That is 0.1.
0.25. Because look, we say that you have a 9 millimeter square area. If you have a 9 millimeter square area, and then it means that this side has been divided into 3. So this side is 1 millimeter square, and this is 1 millimeter. This is a corner square. This corner, these are the corner squares. You should be able to calculate the length here, because this whole thing is 1 millimeter. If it has been divided into 4, you are dividing the 4 into what? You are dividing the 4 sorry, you are dividing the 1 by 4. You get 0.25. So this side will give you 0.25. And this one side is also going to give you 0.25. So you can calculate the area here. Watch here. What's the difference between the lines here and the lines here in the center one? Hurry up, hurry up, hurry up. Our time is almost up. We must finish. Here, watch carefully. This side, okay, what is this side? The length here, what is it?
It's also 1 millimeter.
1 millimeter. But instead of dividing it into 4, it has rather been, the center area has been divided into 5. Watch here. This is 1, 2, 3, 4, and 5. Okay, so this side has been divided into 5. This side is also 5. So it means that this side has broadly been divided into 25. So what will be the size here? The size here. The size here. What will be the size?
0.2.
0.2.
2.
0.2, great. Please, if you don't understand anything, let me teach you, because people just use this one just anyhow and they don't understand the basis. So this side has been divided into 25. It means that each side has been divided into 5. And it is still the 1 millimeter square. Okay, it is still the 1 millimeter square. So it means that one side here is 0.2. Now, this side, which is just 0.2, have been subdivided into 16 smaller squares. This side, which has been divided, this small side, which is 0.2, has been subdivided into like 16 here. So it means that this side is the smallest square. What is it? What is the length of the smallest square?
It's 0.2 by 0.2. If we are taking
No.
Grandpa, you mean the
Yeah, I'm saying that, look, this side, and unfortunately the pointer is not this side. What is the size or the length here? What is it? Anybody to help me?
Grandpa is 0.2.
0.2. And I'm saying that this small square here, has also been subdivided into 16 smaller squares. So what will be the size of the smallest square?
0.01.
No. Come again. Why are you leaving this into one person alone? Somebody should also come in.
0.04.
No. No.
0.0125.
No. See, you appreciate that this side is 0.2. Do you appreciate that?
Yes, please.
Yes.
Because this side has been divided into 25. So it means that one side has been divided into 5 sections. And this side is the same 1 millimeter. So it is the 1 millimeter, 1 divided by the 5, which will give you 0.2. So this side is 0.2. But this side has been subdivided into 16. So that it means that each side here has also been divided into what? How many? 4. Is that not it?
Yes,
So
please.
it's 0.2 divided by the 4. And it's going to give you 0.05. Calculate that one and make sure that you understand it. Do you understand it?
Okay, okay.
Do you get it?
Okay, yes, please.
So
You get
what
it.
will be the area of the smallest square? The area of the smallest square. What will be it? The area of the
0.
smallest.
It will be the 0.05 times the times 2.
Is it times 2?
Yeah, it's twice that.
But times 2 means 0.05 times 2. It is 0.05 squared.
Squared, yes, please.
0.05
Okay.
times. And what is that?
That would be 0.0025.
Good. So now you understand the value here.
Yes, please.
Okay, so the value here is telling you that the smallest square under the chamber is 0.0025. And I just wanted you to just you yourself calculate it yourself and get it so that you appreciate it. That's all.
Yes, please.
Good. So that's all that we're talking about. That's all that we're talking about. So now the calculations, now that you understand. Now, normally counting is done at the 4 corner squares. All of us know that. Is that right? The 4 corner squares. Now we are going to go through. This is the hand tally counter. So that once you are counting the cells under the chamber, you'll be using this one to just in one hand and then just be tapping on it and then tallying it. So this one, for the preparation, you want to do a dilution. The sample have to be diluted. You have to dilute it so that the viscosity will be reduced. Okay, we've said this over and over again. Dilution makes the sample less viscous to allow the suspension enter the chamber smoothly by capillarity action. All right. Also, there's usually large numbers of sperm in the semen sample. So as we dilute it, we dilute the numbers, and then the numbers become manageable to count. All right. Now, I'm sure all of you, one way or the other, have gone through or used the neighbor county chamber before. All right, so you should be able to assemble the chamber. Assembling the chamber is that this one you can wash. You can wash the chamber. You can also wash the cover slips and then get it clean. And then you apply the cover slip on this thing. Have you seen the Newton's ring before? Once you are using the chamber, have you seen the Newton's ring before? How many of you have actually used the county chamber before? The neighbor county chamber? How many of you have used the neighbor county chamber before? All right. So, Bernard. Are you telling me that nobody has used the chamber before? Clement, have you used the county chamber before? The hemostatometer?
No, sir.
You haven't?
No. Yes,
Hey.
sir.
Who has used it before?
I've used it before, but I've not paid attention to the Newton's ring. Hello, Grandpa. Hello, Grandpa.
How do you apply the cover slip on the chamber?
Slide it over the
right. Slide over the chamber. That's correct. But you see, you need to slightly wet the size of the chamber. And then as you slide the cover slip on it, you will see some rings there. That's what called Newton's rings. And once you see Newton's ring, it affirms that the cover slip has been properly fixed on the chamber. That's all. If you don't see anything, it means that it's not secure. And so even if you pick up the chamber and then you turn it, you see that the cover strip will just flip off. Hello, are you following me?
Yes, please.
Hello. Yeah. If you, the reason is that you see, as you got with the macula, you see that the cover slip is a heavy material. All right. And so once you get it there, the depth of the chamber, you can't do anything about it. It's fixed. But with the Newton's, sorry, with the neighbor's county chamber, if you don't apply the cover slip very well, what it means is that you are not going to get a firm depth. It means that the depth will can keep changing. Is that not it? Because
Yes,
it's not
please.
well fixed on the distance. What it means is that if you charge the chamber, you put the suspension down there, it means that the fluid can even lift the cover slip up. Is it not possible?
It's very possible, sir.
So once the fluid is able to raise the cover slip, what is it doing? It's increasing the volume. But remember, you are also going to do your calculation and apply volume based on the dimensions that you have. So those are some of the technical challenges that come along. All right. But once you are able to apply the cover slip very well, and once you see the Newton's ring, or you see some small rainbow sort of things, not a big rainbow, but you see some colors at the edges, straight away it tells you that the cover slip is well fixed on it, and therefore it gives you the assurance that the depth is the 0.1. All right. So once you are introducing a sample onto the chamber, unlike the macula, I'd say the macula is very simple and very easy to use. That one, you are just applying the drop into the chamber. Without, there's no hassle about it. This one, you have already applied the cover slip, and then you are going to apply the specimen in between that small space. And the small space is the depth of the chamber, which is 0.1 millimeters. All right. And so sometimes it's a challenge, especially if you are if you are learning how to do it. Before you could say Jack, you even break the cover slip. All right. So putting the specimen there is, we say you are filling the chamber, or you say you are loading the chamber, or you are charging the chamber. It's the same thing. These words can be used interchangeably. You can fill the chamber, load the chamber, charge the chamber. It is the same procedure. All right. And if you happen to have the V shape, this one, that makes it very, very simple. You just put it where the V cut is, the specimen there, and then to flow automatically into the chamber. All right, good. So here you are supposed to place the once you have charged it, you are supposed to place the preparation there for about 35 minutes for the content to settle. That's all, as you do for anything. All right. So as much as possible, avoid overloading. If you overload, what it means is that the volume that is going to use to charge the chamber is going to be more than what you are using. Meanwhile, you are going to do your calculation based on the dimensions which have been given to you by way of the squares, and also you know that the squares are fixed. All right, the squares under the chamber, they are fixed. What about the depth? The depth is also supposed to be fixed. So you are able to calculate your volume. But if now you are overloading it, that means that the volume that you are going to use, you get a wrong result. Okay. Similarly, underloading the chamber will also create a problem, because you are supposed to charge the chamber in a manner that you are going to get the exact volume that you are going to use for your calculation. And one of the things that can prevent you from actually loading properly is air. If you introduce air under the chamber, then it's going to create a whole space which is not filled by the fluid, and therefore that will account to undercharging. So those are some of the things that then after that you are going to do your counting. Now let's see how you go to your counting. By the grace of God, I'm sure we'll be able to complete this one very soon. You see that this the corner squares, okay? Now, do you know the batterment technique? Batterment. Anybody has idea what is batterment technique? Hello.
Aye.
Anybody has heard about batterment technique before?
Yes,
Okay.
Grandpa.
What is it?
I think it's a way of moving across the field so that you don't
Fantastic.
repeat where
Fantastic.
you.
Fantastic, great. Or you don't miss any portion, especially if you're doing if you are evaluating or assessing or examining stew. If you make a stew preparation and you are examining, if you don't use the batterment technique and you are just scanning it through, you are going to miss a lot of the areas. But this is the batterment technique, the one you have here, so that you start from one corner of the slide, you just go systematically to the next corner. You count down a little bit and then also move this way, move this. This is what we call the batterment technique. If you don't use that one, especially when it comes to a sperm count or any cell count under the chamber, you are going to miss out, because you are supposed to, you see, this is the squares on this is the entire the corner square. This is the entire corner square. Under the entire corner square, you have smaller squares. Okay, so if you don't move step by step this way, come down, go here, and then you want to just do it anyhow, you are going to miss some of the squares and also miss some of the slides. So this is the technique called the batterment technique, and it's very, very recommended, especially in scanning two wet mouse for parasites. Okay, so it's the same procedure. So you start from one corner, go this way, come down, blah, 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 and then you are done. Okay. Now, this is the counting rule. Remember, we talked about the borderline counting rule. Now, the counting rule is just helping you to avoid counting a sperm or a cell. We have told you that the principle of the counting of the sperm using the neighbor chamber is the same principle used in counting white blood cells. The same principle used in counting cells for CSF or any body fluid. The same principle. But like I've said, because these days people are using the automated analyzers, they don't do cell count. Okay. So once they don't do cell count, it becomes very difficult to take you to, otherwise this one should be like, I shouldn't even talk about this one because it will be presumed that you know it already. Okay. Now, so with the counting rule, remember we said that for each corner square, like this one, you have 16 small squares. And so it is 4 squares here, 4 squares here. That will give the 16. Now, a way to know the borders is that for each square, the borders are marked by 3 lines so that you don't count beyond. I hope that point is clear. This is what makes the improved counting chamber different from the, you see, we have an ordinary neighbor counting chamber, and then we had the improved neighbor counting chamber. The improved neighbor counting chamber only introduced these aspects where the borders of the corner squares were now made like triples, so that as you are counting the squares, as soon as you get double lines or triple lines, you know that you have gotten to the end. Okay, so that you don't count beyond this square, for example. How that point is clear. That is the only difference between the improved counting chamber and then the ordinary counting chamber. Now, so this is your corner square with the counting rule is that when cells lie directly on or touch the line, use the counting rule to avoid cells being counted twice. Cells touching the top and left lines of the counting chamber are included. Cells on the bottom and right side are counted out. I hope that point is also clear. So you can even make your own decision that, cells left and down, I'll count them out. Cells top and right, I'll count them in. That's all. You can make your own determination. You can make your own determination that cells lying here, here, and here. For example, as far as this example is concerned, cells lying here, left and then top are counted as part. Cells lying down and right are counted out. So what that in that case means that when assuming this were a sperm or any cell, then it will be counted as part of this square. This one will be counted as part. This one will also be counted as part. This one will be counted as, so that the lines on top and lines on the left, cells lying on them are included. Then the other two sides will also be excluded. It means that the cells lying down here, for example, this one will be included. When you are counting cells here, this one will not be counted. This one will also not be counted. This one will not also be counted. This one will not be counted because you have set your own rule that you are including those left and then the top, and then excluding those right and down. That's all. So that should be your heart. So this one, the same thing. If you are including left and top and excluding right and down. So all those cells here, lying here, you count them in. All those here and here, you count them out. As simple as that. Good. Now, I will also take you through, and remember I said that you have the 4 corner squares. Okay, that's where you normally do your count for sperms or any WBC or anything. But you also have the central area. The central area gives you a very interesting dimension. All right, watch very carefully, and when it comes to calculation, you appreciate it. Here, we are also advised to take within the central square. You are advised to take any 5 squares and count. So 85 squares, you can take the 4 corners of the central square and then take the middle one. That will give you 4 squares. Remember, the dimensions here are different from the dimensions at the corner square. This is the central square. Okay. Now, you can do it this way or also that way. So 1, 2, 3, 4, 5, any 5 squares, just as under the macula. Remember, under the macula, you are taking any 10 squares. So you can decide to choose any 10 squares, either down diagonally or across or whatever. This one too, you can concentrate yourself on the central square area. Remember, the dimensions in the central square area are different from the one in the corner squares. And then over here, you choose 5 squares, either this way or that way. And when you do the calculation, you also appreciate the calculation as from this point. Remember, the things to do once you have done the accounting, then you'll be there. You have to do your calculations. The things that you require to do your calculations are as follows. 1, you have to note down the number of sperms you counted in the 4 large corner squares. And know that you are supposed to count the sperms or the cells in the 4 corner squares. So all the 4 corner squares, the cells that you counted, just note them down. Okay. Remember, you also will do dilution factor. Remember, if you have a sample and I make a 1:2 dilution, okay, 1:2 dilution of a sample, and of the 1:2 dilution of the sample, I've got 20 cells in it. What will be the number of cells in the undiluted sample? I take a sample, I make 1:2 dilution, and out of the 1:2 dilution, I got 20 cells. What will be the number of cells in the undiluted sample?
Number 40.
Great. So you make my work very easy. So the number of cells you multiply by the dilution factor, that's all. So if I make 1:10 dilution and I get n number of cells, I'll multiply my n by the 10. If you get any dilution factor, to get the entire value, you multiply it by the dilution factor. Simple. And so thank you very much. So you also, but remember that you determine your own dilution factor based on your initial assessment of the wet mount. Based on the initial assessment, when you can decide, oh, as for this specimen there, I'll do 1:2 dilution. Oh, I'll do 1:10 dilution. I'll do 1:20. I'll do 1:40, and so forth. And so you determine your own dilution factor. All right. So you have and then the total volume of the chamber. Now let's go back to another calculation. Take your pen and paper. Take a pen and paper. Now, remember that we said, good. Let me go back. Okay. So over here, still let me go back again. Okay. So these are your 4 corner squares. Okay. 1, 2, 3, 4. 4 corner squares. What will be the area of this corner? The number 1. What will be the area? Please help me because you've done very well already with the calculations. What will be the area of the corner square here? Number 1, the area. Are you sleeping?
W.
Now then what is the area? What is the area here? This square, corner square. What is the area?
Where is your pointer?
My pointer no ayro. Pointer me ayra kura me why. Pointer na ayra. Maybe I mean my pointer. Let me go here and see. I'm trying to see if I can get a pointer. Okay, Saba. Hey, Marco. Let's see. Okay. So this now you can see the pointer.
Yes,
hello. Sir. What is the area here? The area here, one corner square. What is the area there?
That's the small one is 0.25.
That the area here, the corner square, one corner square, the area. The area is 1 millimeter square.
Yes, 1 millimeter.
So the whole here, the whole thing is here 3 millimeters. So
Sure.
this side will be 1 millimeter. Multiply by under 1 millimeter, give you 1 millimeter square.
Sure.
Good. Now, the depth of the chamber is what? The depth of the chamber is 0.1.
0.1.
0. So what will be the volume here? The volume here. The volume here. Hurry up. Hurry up. The volume there, here. The volume here will be the area, which is 1 millimeter square, multiplied by the depth, which is 0.1. And so the volume is going to be 0.1 millimeter cube. Is it difficult?
No.
So the volume is, remember, you are going to count the number of cells where 4 corner squares. The volume here, is it different from the volume here?
No, it is not. So
if I'm counting the 4 corner squares, what will be my total volume? The total volume that I will have covered.
0.4.
0.4, very good. 0.4 millimeter cube. So if I count any number of cells, when I say n, you know it's a variable. So if I count any number of cells in the 4 corner squares, it will be 4n in, as we did with the macro, n in 0.4 millimeter cube. Is that all right?
Yes, please.
And so that is going to give me n over 0.4 millimeter cube. Is that all right?
Yes, please.
Good.
Yes.
And we know that millimeter cube is the same thing as microliter. So it's going to be N over 0.4 microliter. Is that all right?
Yes.
Are you? It should be one person or all of you. So if I count the number of cells in the 4 corner squares, and I get N number of cells, to be N in the 0.4 millimeter cube. So N in 0.4 millimeter cube means N over 4 over 10. Do you also appreciate that? Just as we did with the macula.
Sure.
And that is
Yes.
going to be, that is now going to give us N over 4 times 10 per microliter. Is that also okay?
Yes, please.
Good.
Yes, please.
Okay, good. So coming back, so it gives me N over 10 times, sorry, N over 4 times 10 per microliter, as we did with the macula. We are going to count sperms in what? The number of sperms in the sample, not, remember this N number of cells that we got were from the diluted sample, is that not it? The number of cells that we got
yes,
here, is
please.
it from a sample or from a diluted sample?
The diluted sample.
So it means that our N must be multiplied by the dilution factor, is that not it?
Yes.
Good.
Yes,
So we
please.
are going to get N times the dilution factor. N times the dilution factor, assuming that we did 1 in 20 dilution, there's going to be N times 20 times 10 over what?
Over
Over what?
4.
Very good. Over 4
4.
and then microliter. Is that all right? Good. Now
Yes.
we know that we want our number of sperms per mil, not in microliter. So to convert the microliter to mil, as we did with the macula, we must also now multiply by 1,000 and convert the microliter to per mil. Is that all right?
Yes, please.
So you are going to get N times 20 times 10 times 1,000, which is 10 to the power 3 over 4 then per mil. I ask you to take a pen and paper. I'm sure you have it. So what do you do now? We have N 20 times 10 times this. So our 4 can cancel the 20 and we get what?
5.
5. Good.
5.
So the whole thing now becomes N times 50 times 10 to the power 3, which is 1,000 per mil. Okay. Good. Good. We want our results in million per mil. We already have 10 to the power 3 here. Is that all right? So what again do we need? We need another 10 to the power 3. Is that all right?
Yes, please.
Good. So we must manipulate the 50 to give us 1,000. How do you manipulate the 50 to give us 1,000? Instead of the 50, if you write 1,000 over 20, are we still maintaining our 50? If we divide the 50, if we have N times 50 times 1,000, okay, or 10 to the power 3 per the mil. I say that we want our result in million. Million means that we should get 10 to the power 6. You already have 10 to the power 3. What can we do to get a 10 to the power 3? So that's a mathematical manipulation. So we are converting our 50 to 1,000 over 20. Does it change anything?
Doesn't change it. No, it's the same.
Good. Good. So it becomes N times 10 to the power 3 times another 10 to the power 3 divided by what? I want to know whether you are following it. 10 to the power 3 times another N times 10 to the power 3 times 10 to the power 3 divided by what?
20.
Good. Great. Clap for yourself. So you have the 20 there. So the 10 to the power 3 that 10 to the power 3 now gives me my million. 10 to the power 6 gives me 10 million. So what it means is that if I do a Y in 20 dilution of any cell, whether it's semen sample or blood sample or whatever body fluid, and I want my result to be in per mil, what it means is that whatever number that I got from the 4 corner squares, I should divide by 20 and then now add my 10 to the power 6, which is the million per mil. That's all. That's all. That's all. So whatever number of cells, if you did Y in 20 dilution and you counted the number of sperms in the 4 corner squares, whatever number that, if I got, let's say 300 from the 4 corner squares, I should divide the 300 by 20 and just add million per mil. If I got 200, I should divide by 20. If I divide 20 by 200 by 20, I think it's 10. Eh? So it means the result is 10 million per mil. That's all. So that is all about the hemocytometer. If you get this principle, you can do anything that you like. You can do anything that once you get the principle correct, anything. So for example, this is a typical example. Here's here the 4 corner squares. This side we got the corner C, the C corner we had 4 cells. The D corner we have 3 squares, 3 cells. Here too you have so total number of 14. Okay, total number of 14 cells. Now, if you did a Y in 20 dilution before we did the before we did the dilution, then by the calculation, I think I've taken you through all this. By the calculation, it is going to be the 14 that we had divided by 20. Okay, 14 divided by 20, and then million per minute. That's this all the long thing here is what all that we did. So we are going to get the 14 here divided by the 20. Okay, 14 divided by 20 will gives you 0.7, and then this one becomes a constant. 10 to the power 10, 1,000 to 1,000 gives you a million. So the result becomes 0.7 million. Once you take your time and go through, I think it becomes very easy. Okay, right. So the general rule is that to do a sperm count, the number of cells that you counted multiplied by your dilution factor divided by the volume that you counted. That's the principle. The volume within which you did the counting. That is all. That is all. So this is once you get and go through. So I've made a table here. If you did a Y in 2 dilution, okay, and you can take your time and also do this one yourself so that you grasp it. If you do a Y in 2 dilution of a semen, then if you did a sperm count from the 4 corner squares, the number of cells that you get divide by 200 and then add million per mil. If you did Y in 4, if you come to the Y in 20, you see that you get the number of cells divided by 20 million per mil. If you did Y in 80 dilution, number of cells that we counted divide by 5 a million per mil. All right, so it is also simple if you understand it. The rest is just all this. Right, now let's take the center square. Okay, the center square, the dimension here, what is it? The dimension here, what is it? Please,
The 0.2.
Very good. So the area here will be what? The area here will be what? 0.2 multiplied by another 0.2. That will give you 0.04 millimeter square. Okay. This one will give you 0.2 multiplied by another 0.2. That will give you 0.04 millimeter square. Now, the depth is still constant. The depth is still constant. So the depth is another 0.1. Is that not it? The depth of the chamber is 0.1. So the area multiplied by the depth is 0.1. So if you multiply the 0.04 by 0.1, That's going to give you 0.004 millimeter cube. Okay. Now, if you take 5 squares from the central area, each square will give you 0.004 millimeter cube. So if I take 5 of it, I should multiply the 5 by the 0.004, and that is going to give me 0.02 millimeter cube. So it means that if I count n number of cells in the 4, it's going to give me the n over 0.02. Okay, it's going to give me, and if you do the calculations as we did, you realize that at the end of the day, the number of cells that you count in the 5 corner squares here, just as we had with the macula, just add what do you call it? This thing is rubbing too, so ignore it. So if you multiply the volume here by 5, and you did the calculations as I went through with you, you are going to get n multiplied by 1,000,000. Okay, so in that case, any number of cells that you get from the 5 corner squares here, as you did with the macula, just add million per mil, and that's all. So if you counted, you took the central area and you counted the number of sperms in the 5 areas. If you got 50 cells in the 5 here, it's 50 million per mil, and that's also very simple. You can go through if you get a slide, and then these are some other additions that can help you too. So total sperm count is the sperm concentration as you've gotten multiplied by the volume. It is very, very simple. Total ejaculate is the volume as you have gotten. You know that volume I've taken you through. We are no longer going to aspirate anything. Volume, pre-weigh the container, give it to the patient after the sample has been collected, weigh it again, subtract the weight of the container from the weight of the sample, from the new weight, and then just subtract. You are going to get the weight of the sample itself. The weight of the sample is equivalent to the males, the volume proportion of the distance. As simple as that. As simple as that. So multiply that volume by your sperm count, and that is all. That is your volume, total volume. Right. So once you're able to do this one, this is just something to help you to avoid errors. So once you are done, if there are no sperm, that's azoospermia. I'm going to take you quickly through cryptozoospermia, and then if cells are less than 15, it is oligospermia. If it's within 15 to 200, nomospermia, even though sperm count can be up to 259, but any count more than 200 is called polyzoospermia. Polyzoospermia. All right. So this is something that you can also read: parameter, normal sperm, and then the variation. Cryptozoospermia. Remember, we said that if you do a wet mount of your semen sample and you don't see any sperm in it, don't conclude. You can only suspect azoospermia. If you don't see any sperm in your wet mount, please don't conclude azoospermia. You can only suspect azoospermia. There is a condition called cryptozoospermia. That's what we're going to. Crypto means hidden. Just as you did with cryptorchidism. You know that cryptorchidism is where the testis is supposed to be the scrotum. So if it is no longer in the scrotum, it means that it's hidden somewhere. That's cryptorchidism. All right. So crypto means hidden. Now, so when you have cryptozoospermia, it means that the sperms are hiding somewhere. So that you did your wet mount, you didn't see any sperm in there. So what you do is that you know that semen has a semblance with blood. And the semblance is that once you spin blood, you are going to separate the cells from the plasma. Okay. So if you also centrifuge semen. You are going to separate it from seminal plasma from any cells that are in there. So you did your wet mount, you didn't see any sperm. Don't conclude as a spermia until you are finished with this one. So you take some sample, some of the sample, and then you spin as if you are going to do urine. You spin, you take just our 1 ml of the alicot, spin. When you are finished, just examine the deposit. If just as if you are doing wet mount, urine, if you go through the deposit and you don't see anything, then you conclude that it's azoospermia. You make a diagnosis, a confirmed diagnosis that it's azoospermia. If from the centrifuge deposit you see even a single sperm, whether it is dead or alive, there's I'm told that there's a film called Bring Dead or Alive. If you get the even a single sperm in the deposit, it is not azoospermia. It is what we call cryptozoospermia. Okay, so you will report cryptozoospermia. That's why you're not going to do count because you did a deposit and then you saw a sperm. You are only concluding that the patient is not exclusively devoid of sperm. That a sperm said that is not enough, and that is what we call cryptozoospermia. Ladies and gentlemen, this is all I have for you, and I'm sure the rest as you go to, if you want to do semen culture, I think I have some few slides here for you to that can help you. So more on the terminologies. Aspermia, you know already. Aspermia means absence of the semen, not azoospermia. It's not the same. So aspermia means, and that is where you can talk about complete retrograde ejaculation. Okay, right. Azoospermia is where there's no sperm after centrifuge, after centrifugation. Hypospermia, low sperm, low ejaculate volume. Hyperspermia, high ejaculate volume. Necrozoospermia, necrosis. I'm sure you know about necrosis. Dead. Said necrotic. It means it's dead. Necrotic tissues and so forth and so on. So necrosis means dead. So if all the sperms are dead, we say that that's necrozoospermia. All right. And then, of course, you know this already. Hematospermia is when you know this one, globozoospermia, where you have round headed cells. Pyospermia or leucospermia, you know that when you have fast cells. And then oligo means lower sperm count, less than 15 million per day. Polyzoospermia, I've told you, when you have more cell count, more of the sperm count. Nomospermia, when all the parameters are normal, the comment to make is nomozoospermia. Everything is normal. Your sperm, your count is normal, morphology is normal, motility is normal, everything. So make a comment that everything is normal, and the word to use nomozoospermia. Acino, you know already. Acino, when the motility is lower than normal. All right. And then terato is when morphology is also very low. When you say terato oligozoospermia, terato is abnormal morphology. Oligo is also lower count. So once you have lower count with abnormal morphology, then you can combine that as terato oligozoospermia. When you have actinoteratozoospermia, it means that lower motility and also lower morphology combined. And then oligoactinoteratozoospermia, I think I mentioned this to you already. This is called the oat syndrome. So oligo means lower sperm count, actino lower motility, terato lower morphology. So when you have low, all the things are low. That is oligoactinoteratozoospermia. That's what we call the oat syndrome. Okay. So when it means that the terminologies can combine them. So if you have pyo-oligoactinoteratozoospermia, it means that you have low count, low motility, lower what do you call it? Lower morphology, and then also a lot of parts in there. So that's pyo-oligoactinoteratozoospermia. You can combine them. Of course, you know that cryptozoospermia is semen that contains few sperms that could not be counted for. And then this is just a sample of some routine reports. You can just quickly go through this one. And then this is, let me now take you through the your report, the way to report. So report format. So you have a patient name, date. So I have given you this format, and you can also adapt it to suit your lesson. But something like this one will help you to have a very normal Semen analysis report format. So this is your template for you. The name of the patient, date of birth, and age, if you have any of them. Partner's name, because most of the time it is the women who bring the samples. So it will be good to also have their names recorded. All right. So partner's name and then partner's date of birth. Of course, for every sample must be accessioned, and that is it must be ID. Date of sample collection, clinical diagnosis, referring health facility, where is the sample coming from, and which doctor is also making the request. All that is also very important. And then the patient sample information, abstinence period, place of production, where was the sample produced? You know that where the sample was produced also give you idea whether the sample should come to the lab early or not. So place of production, if it's at the lab, if it's at the lab, just take care. If it's not at the lab, then wherever it was, if it's at home or in a hotel or also write it. Okay. Method of collection, masturbation, or coitus interruptus, withdrawal, or special condom, or anything. All that is very good. And then complete collection. Was the sample collected properly? Ask the patient. So was it completed? If it's yes, leave it there. If it say, oh, something, I think something spilled over a little bit. So if it means that the sample was not complete. If it's not complete, you need to further probe the patient to find out. So is it like at the time that you are going to put it in that some fell, or the last portion, or whichever? So you also indicate all of that. So if no, it means that the sample was not complete. And then in that case, you have to now, what part of the sample is missing? Is the first part, middle part, or last part? You know that any of this part missing or give a fair interpretation of the report that you have to write. And then time of collection, then time sample received. And then other patient information, you know that you have to ask the patient in the last couple of months whether he has had some severe infection or inflammatory disease. If it's yes, you need to indicate it, because all those things will be useful once you want to interpret your report. And then time of the analysis, you need to. Then from here, this is a good report format for you. Ejaculate volume, you indicate this is the reference ranges as defined by WHO 2021. All right. So ejaculate volume, the pH, although you write it. So these are the reference ranges. Viscosity is also there for you. Your liquefaction, the time it took for complete liquefaction. Was it said that, or the sample said that you needed to treat it? Remember, we said that when the sample is too viscous, you have to treat it either mechanically or by addition of some chemicals. And if that is the case, you need to also indicate. If nothing like that, so the yes or no is just to also help you what to write them. Now, of course, the motility, progressive, everything that. So this is a good format for you to use in your labs. All right. All right. So everything is there for you. And then the comment. Here I'm saying that based on the results of the Semen analysis, appropriate comment on the results can be made using the appropriate terminological or hematological terminologies. The terminologies, as you said, whether it is O syndrome or whatever, you just then when you finish, who analyzed it? After the analysis, somebody must validate the report. That's common for all laboratory reports. Somebody must have analyzed, somebody must validate. All this information should be there, and that makes your this thing very, very good. And so the rest is just references for if you want to make some references. Thank you so much, and I'm sure the last part has been very, very technical, not very mathematical, but I'm always available if anybody has anything he wants to also. You can call me at any time. Take your time to go through the calculations with the neighbor counting chamber. You use that also for any other cell count, whether anybody fluid, any, especially CSFs, they will normally request for cell count. And the same principle, the same neighbor counting chamber that you use, you may use a diluting fluid to dilute, except that that diluting fluid is normally the WBC diluting fluid, which is the text fluid, which you also mentioned. So that is all. But the principle, everything is the same. All right. Thank you so much for your time. I think as far as I'm concerned, we have gone far in this program, and this is where we will end. Once again, thank you so much. Now and Kingsley, as class reps, you can put your heads together. If you think that there's a need for us to meet for practicals, fine. Otherwise, I think that is okay. End it here, and we give ourselves 2 weeks to prepare for the final exams. All right.
Grandpa.
Yes, sir.
Please, with the counting, I want to ask question on it since now
Please
we
do.
have made.
Please do.
People, but when you are counting, are we counting only complete sperm cell? Or
Exactly. You are counting because we said that anything which is not a proper, when you say a proper sperm, a sperm is one which has a head, a neck, and a tail. Anything other than that should not be counted. And those that will go into the detritus, like things, so that will be fragments. If you count a sperm head alone, you haven't counted, it's a detritus. Okay, so you count sperm as it is.
Part of the other morphology, like maybe, I don't know if there is a chance of seeing the double head and double tail. If we are to see some under the chamber, should we count them?
Oh, when you want to do your morphology assessment, the appropriate way is to do a staining. That one, I think we said that already. And I'll strongly recommend that if you want to do any semen analysis, morphology assessment, please, if you can get your eosin, negocin, that would be fantastic. If you can't get negocin, eosin, you can still be using Gimsa or Leishman. And remember that the staining for Leishman Gimsa is the way that you do for any blood film staining. Okay. If you are using Gimsa, it means that you must make sure that you fix your slide very well before you go apply the Gimsa. If you are using the Leishman, it means that just some small initial fixation will still be okay, because the Leishman will also, initial stages of Leishman will also fix the slide for you. All right. So that would be the best approach. Okay. So
what I mean is under the chamber, when we are counting and we see maybe a sperm cell with 2 head or 2 tails, should we
don't count them? They are that's where you want to you see, we have said that as we have defined a sperm. A sperm is a one which has a head and a tail. That is, if it has 2 tails or whatever, they are not sperms. Okay, so don't count them. All those will go into the morphological assessments. You are confused?
No, sir, I'm not confused.
Okay. Count proper sperms, but not. But that count proper sperms doesn't mean that you are assessing their morphology. Even though some people try to use their, of course, some people try to use their experience to do the morphological assessment to even as wet mount. If you have that experience, fine. But for proper evaluation, you need to do your a stain of a sort. The eosin, you can easily get eosin. Eosin is very, very cheap, and then it's available. Anybody who is doing, if you get any friend who is doing hematology, one of their basic stains is H&E, hematodrin eosin. Every hematology laboratory has it. Okay, so you can get some from any hematology lab. Or if you want to buy eosin, you have the eosin Y. That's what you use. You have the eosin B. Don't use that one. The eosin Y. And then nigrosin 2 is also very cheap, except that people don't. The suppliers don't stock items that are not fast moving. That's the problem with some of these things, especially the macra, for example. Nobody will go and buy macra there and put it and stock it once you know that nobody's going to buy it. They don't stock it. Okay, but if you're interested, you want to actually do full scale analysis, you want to also add some kind of value to what you're doing, you can make a special request for somebody to get you a macro chamber. And it's one of the best ways to do your semen count. Okay. All right. Okay. All right. Any other question? So today is, so by the weekend, I'm sure the rest of the slides will be uploaded for you. And you have 2 weeks. Is it 2 weeks? Is it too short for preparation for the final exams?
Grandpa, it's too far.
Come again.
I think it's too far.
Oh,
2 weeks
why?
is too far.
Grandpa,
So you want 1 week. The questions are already. You want 1 week to prepare.
I think
You want 1 week, cry. You can get it. You can get the exam for you next week.
hey, Grandpa, this is critical. This one is critical thinking. For 2 weeks is okay, Grandpa.
So I think somebody said that 2 weeks is too far. Okay,
I
so
think
you have
the practical too. I think that one is very important. If you can do
if you whatever you want me to do, this is what I'm going to do for you. So please, I'm giving you, but we can still
Yes,
do the exams.
we are going to discuss that one on the platform and see the majority that we would like to come face to
Okay,
face and I'll
okay,
let you.
okay. All right, all right. I'm there for you, please. I'm there for you, please. And remember, I've said that anytime anybody wants to call for any further explanation on something, feel free to call, okay?
Hello, Grandpa.
Yes, sir.
Yes, this goes to our coordinators. This is more than a CPD. It's a school on its own.
Yes, sir.
We are very much happy about it. And then with the uploading of the materials, I'll plead with them if it can be done once the lecture has been given. It will help some of us who would always want to go through what we have learned a day before even continuing. It helps us. A chance na nyamaka yetrim intino.
Okay.
It's not book check. So we'll plead with them if
Mate,
that can be done for us.
Mate, I'm sure the coordinator
so
I usually I don't have control over those aspects. That's
sure,
one thing. I don't have control, but
sure.
I'll do my best.
Sure.
Okay.
I'm believing it's because of those who did the delay in payment.
Okay, yeah, it is also true. Okay. All right. It's a pleasure having all of you, and I'm hoping and praying that you have opportunity to meet in person. Okay. I wish you all the best. Yes, sir.
We were able to hold Prof too. Thank you very much.
You're welcome, sir.
Thanks.
Hello, Grandpa. One last thing.
Yes, sir.
Yeah, to some of us who haven't done some before, that you would like to set an andrology department. I suggest maybe by the end of the program, to as part of the benefits of doing just you give us a clue and the things and other. Though you have given us in the process of doing the course, but maybe if we can get a concise one on how to set an andrology lab so that when we get back and we are proposing to management, we will make it interesting and when they are listening. For some of us, we haven't done some before, and we are now going to set it back, and we want to benefit full time on it.
Okay. So what our advice is that the program still virtually is theoretical. Okay. So if you want, you can still, if you want to actually start, you can liaise with a facility that actually already doing it, and a person who has also gone through the program, because there are a lot of people who are doing the semen analysis, and I tell you, they are virtually doing nothing. They are all, everything that they are doing is just nothing to write home about. So if you go and study from such persons, you may have a challenge. But if you go to a facility that's running, and you know that person is already has also gone through training of a sort, not necessarily my training, but some training of a sort, then you know that you are learning from the right source. Then you can start well. Okay, our advice about that one. So, but if you want me to help you anyhow, anyway possible, by way of information about how to get this or how to get, and even sources of some of the things, the materials, or where to get some of them, I can still guide you. Okay. All right. So that is that. If you haven't started at all, you can still start, but make sure that you can have, let's say, a weak attachment with some facility. And that will be very helpful.
Thank you very much.
All right. On that note, we bring the whole program to a successful end. Can somebody pray for us for how far God has brought us?
Grandpa, we are grateful for your support and everything.
I didn't say vote of thanks, so I said pray for us. Christian, are you praying for us, or you are only giving vote of thanks? I say somebody should pray for us for having gone to a successful program.
Okay. Our Heavenly Father, this evening we thank you for giving us the spirit of endurance, patience. Father, this far your grace has brought us. Father, we thank you for all the facilitators and all who brought the program to a start. Father, if we are going to an end, it's by your grace. Father, let us be able to put it at work, what we've achieved today, from the very day to today, so that at the end, we'll say, it is you who have made all things possible. Father, our director and our boss, Grandpa, may you empower him and enrich him with more knowledge so that he will be empowered to do more than. In Jesus' name we pray. Amen.
Hey, Osofo Christian. Osofo, say now you're Osofo.
Amen.
That was a powerful one. Okay, so
Grandpa, we are much grateful. We still contact you.
Okay, you're always welcome. So if you have to assess the program, will you say average, above average? Was it below your expectation or above your expectation or normal?
Excellento, esculento.
Which means
it's beyond what we expected.
This is above expectation,
yes,
Grandpa.
it's above expectation.
It's above expectation.
Okay.
I remember my people will ask me, "Hey, you people are still not done."
Anyway,
Thank you very much.
The time as I'm
Grandpa, I have seen someone doing semen analysis, and after this call, the things you need to do and the way I observed the person doing it, and the result that he produced nicely, I was even shocked how he had the results. So it's like, yeah, it's good. It's good to learn because it's good to learn.
All right. Okay. Bye-bye.
Bye bye.
Uh,